Okay, well, here we are again. At least you can see me this time. We're going to do solubility of gases for this one. And a lot of it's going to be review for you guys, but I got to tell you, I've been teaching chemistry for 41 years, and I hate to teach it if there's no practical application to what I'm teaching you. This, solubility of gases and the gas laws, huge practical applications. From the carbonated beverages you drink to scuba diving. So it's all over. So what we're going to do is we are going to start at the very beginning. This is going to be a review for you guys. And the first thing we have to talk about would be mixtures. And this was the beginning of the year, mixtures. There are two types of mixtures. There's homogeneous mixtures and there's heterogeneous mixtures. The quick way of figuring out which one is which is a hetero mix, it doesn't blend together and it got a layer. So if it has a layer, chances are it's a hetero mix. If it doesn't have a layer and it all blends together and you can't filter it, it's a homogeneous mixture. Now, I hate saying, oh, this is a homogeneous mixture. Just say solution. So a homogeneous mixture is a solution. It has no layers. And remember, mixtures are put together and taken apart physically. And the main homogeneous mixture or solution that we know is this one. So what that means is we're putting salt, which is right here, ionic compound, crystalline solid, in water. And the salt dissolves in the water. No big deal. And you can't filter it. You can't filter salt water. So that's the type of solution that we all think about. But there are other solutions. There is this solution. This is brass. And it's made up of copper and zinc. So they melt copper, they melt zinc, they blend them together, and if you take a sample of top, middle, and bottom, it's all the same. Copper isn't at the top, zinc isn't at the bottom. So this is a solution of metals. So that's this solution. But the one we are going to talk about the most is this solution. And this solution that we're all in is called air. It's a solution of gases. And here's where we really have to understand what's going on. The main gas is this one. Nitrogen gas. About 7% of all the air we breathe is nitrogen. Then we got about 25 maybe, 25% O2. And then we have other different gases that make up the rest, but the one we're concerned with is CO2. Those are the three gases we're going to be talking about throughout this whole solubility of gas thing. So, what I'm going to show you is this. They all have something in common. All three of those gases have something in common. So let's look at nitrogen. Nitrogen group 15 got 5 valence electrons around it, and it looks like this. Got an unshared pair there, single, 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 single. So you have one pair there, and one pair there. So nitrogen looks like that. And one nitrogen can't pull a shared pair closer to it. They both share equally. So if they share the electron pairs equally, it's a non-polar bond. Got it? Non-polar bond. And it looks like this. This is N2. All right? Next one is oxygen. This is the one we're really concerned with. And this is in group 16. Got 6 valence electrons around it. 2 pairs, 2 singles. There's one shared pair. There's 2 shared pairs. That's what it looks like. And once again, these two have something in common. They each share pairs of electrons equally. So that means both of these gases are nonpolar. They're both nonpolar. Now, the next one. Here, pair here, there's a pair here, and there's a pair here. Or it looks like this. But this is different than O2 and N2 because oxygen is wickedly electronegative and it's pulling these pairs of electrons kind of away from the carbon. So it makes the oxygen slightly negative, the carbon slightly positive. So they don't share equally. So carbon dioxide has polar bonds, but it has something in common with O2 and N2. It's symmetrical, which means you can cut it any way you want and it looks the same. So all three of these, O2, N2, CO2, all three of these gases are symmetrical. And if they're symmetrical, all three of these gases are nonpolar gases. Everybody got that? Okay. Now, the next. Now we're going to talk about H2O, probably the most important molecule in the whole world. H2O. O is wickedly electronegative, so it's going to pull harder. So here's what it looks like electron dot-wise. Now notice the oxygen is pulling the pairs of electrons closer to it. So that makes oxygen slightly negative, and that makes hydrogens slightly positive. Now there's a slightly sign, but you don't need to know that in high school chemistry. Now, here's the big deal. They share unequally, so it's a polar bond like CO2, but it's not like CO2 because if I cut it that way, it doesn't look the same on both sides, so water is asymmetrical. Asymmetrical, so H2O is asymmetrical, while N2, O2, and CO2 are symmetrical. That's going to be a problem. Now, so what we're going to talk about now is carbonated beverages. Obviously, liquids that contain CO2. Everybody knows them. Here are some colas, there's sparkling water, there's all sorts of stuff. That just means it has carbon dioxide in it. But that's a problem because most liquids are made up of H2O, which is a polar molecule. And the problem comes in when you have a polar liquid and you want to put a nonpolar gas in the polar liquid. They will not mix. They don't like to mix. In other words, polar liquid and nonpolar gas, you got to push it in there. It doesn't want to stay in. You know it doesn't want to stay in. Because when you open a can of pop, you hear a psh. Well, that psh is CO2 coming out. So why doesn't CO2 want to stay dissolved in the liquid? Because the liquid's polar and the CO2 is non-polar. So they have to do two things to keep this liquid carbonated. How they get the CO2 in there in the first place? They put it in under pressure and then they close the system up. So the CO2 is trapped in the polar liquid. But then when you open up the cap and you hear that psst, that's the non-polar CO2 wanting to escape. So we don't want it to escape. It's called the soda or whatever going flat. That means it has no more CO2 in it. So how do we keep the gas CO2, which is non-polar, in the polar liquid? Two ways. We keep the lid on tight, which is high pressure, and we put it in the refrigerator to keep it cold. Now we've gone over two things, how to keep a gas more soluble in a liquid. High pressure and low temperature will keep even a non-polar gas a little bit more soluble in a polar liquid. But eventually, what's going to happen is this non-polar CO2 will eventually escape and the liquid turns flat. We've gone over that before. I hope you understand that. Okay, now let's go from a carbonated beverage that we're trying to put non-polar CO2 in a polar liquid to a lake trout. And yes, Mackenzie, this doesn't look like your normal lake trout. I think it's a lake trout from a lake near Chernobyl. I don't know. Anyhow, lake trout, any type of fish needs dissolved oxygen from the water to live. Remember, oxygen is nonpolar and water is polar, so they don't really like to mix. So where would you find a lake trout in the lake in the summertime? Well, since more gas can be dissolved at high pressure, low temperature, you would find them at the very bottom of the lake. Why at the bottom of the lake? Because of two reasons. High pressure and low temperature. High pressure and low temperature, the gas, even though it's nonpolar, will be more soluble. So there'll be more dissolved oxygen the lower you go in the lake. And that's great. That's why lake trout, or a lot of fish, if it's a shallow river in the summertime and it gets too hot, well, you don't have high pressure and you don't have low temperature, you have the reverse. You have super high temperature and very low pressure, so there's hardly any dissolved oxygen in the water, and that will kill the fish. So, that's the solubility of a gas, a nonpolar gas, in a polar liquid. High pressure, low temperature will help put the solubility of a nonpolar in a polar liquid. Okay, so we just went over the solubility of a gas in a liquid, a nonpolar gas in a polar liquid. Very difficult to get in there. Now we're going to do a little bit about Boyles Law. I've been scuba diving for over 40 years. I started my junior year in high school. We've been all over the world. And if you don't know this law, yeah, you won't be around for long. Boyles Law is pressure and volume. So just think about this. As you go down into the water column, the pressure increases 1 atmosphere every 33 feet. So the pressure is increasing as you're going down. But that is decreasing the volume. So you have a perfectly indirect relationship. As the pressure goes up, the volume goes down. Now, why is this important to know for scuba divers? It's hugely important to know. Because remember, if you're jumping off you take a big breath of air, jump off the diving board, you're going down into the pool, the pressure is increasing, you can feel it in your ears, but the volume of air in your lungs gets smaller. You touch the bottom, you come back up, the pressure decreases and the volume fills your lungs again and everything's cool. But in scuba diving, when you go down, you fill your lungs up with air at depth. And if you don't remember Boyle's Law, you could be in huge trouble, mostly death. And especially if you are coming up, if you're ascending from the water column, you know that the pressure's going down. But the volume of air in your lungs is expanding. So the big deal is breathe normally on the way up. Because if you hold your breath, as you go up to the surface, the pressure decreases, the volume increases, and if you're holding your breath, the volume increases, and you could burst your lungs. And that is very dangerous. In fact, it leads to death a lot of the times. So, Boyle's Law, the #1 law in scuba diving. So amazingly enough, Boyle's Law also affects fish in the ocean and in the fresh water, especially bony fish. There's two types of fish. There's bony fish and there's cartilaginous. We'll first go over bony fish, like this picture I took of this barracuda. Most bony fish have something inside them called an air bladder. This air bladder, they put air into it and it makes them buoyant, or they take air out and it sinks. So the first time I came across this is when I was fishing, deep sea fishing off Florida. And it was way down, maybe 150 feet, 200 feet, and I reeled this fish up really quickly. And when I got to the surface, everything on the inside was coming out its mouth. And I said, what the heck happened here? I don't understand it. Well, what happened was, if you reel a fish in from very, very deep and you reel it in real fast, the air is going to increase in volume because the pressure's decreasing in volume. So Boyle's Law will take into effect, and the air bladder will expand so much that it pushes everything else out its mouth. Pretty nasty. Now, you've all seen goldfish and any type of fish in an aquarium perfectly still in the water, perfectly buoyant, not going up, not going down. Well, that is because of the swim bladder or the air bladder. So once again, that's Boyle's Law taking effect. But I talked about two types of fish. One was bony fish and one was cartilaginous fish. So, cartilaginous fish are sharks and rays. And that means they have no bones. They're all made of cartilage. And the deal with sharks and rays, they don't have an air bladder. So the minute they stop swimming, they sink. So mainly it's the big sharks that happens to. Now this is a hammerhead I took a picture of off Coco Island in Costa Rica. And they were swimming all over the place, as you'll see in a second. They are schooling, and there they are schooling. Now, sharks are cartilaginous, so are stingrays like this. And they don't have swim bladders. This is Michelle getting nailed by a stingray up and over the head, looks like a hat. So the stingrays basically stay down below, but there are some sharks that don't have to keep on swimming. This is a nurse shark. That's one of the sharks. It just rests at the bottom most of the time. A couple more sharks, a Port Jervis shark, which is like the oldest shark in the ocean, that just rests also, and white-tipped sharks, which will be coming up in a second. They're like the couch potatoes of sharks. They can just rest on the bottom until nighttime, and then they kind of go crazy feeding. But no swim bladder. Most sharks have to keep on swimming, or else they will absolutely sink to the bottom. And no water going over their gills means they will suffocate because no O2 into their system. But there's another thing that we have to talk about that we didn't discuss yet, and that's the solubility of a gas in a liquid. Like at the bottom of a lake, you have high pressure, low temperature, you have So, we're back to solubility of a gas in a liquid. But we're talking about air in this tank, right here. It's 70% nitrogen, 25% oxygen. Okay? Now, the deal is, the deeper you go, the more pressure you have on you, and the colder the water temperature is. Perfect conditions for dissolving gas. But this time, it's perfect conditions for dissolving gas in your blood. So that's what, these two things are dive computers. They tell you the percent of nitrogen that they think is in your blood. Now, why nitrogen and not oxygen? Because the air you breathe is 70% nitrogen. So we're very concerned about nitrogen in your blood. This is way different. So what happens is, you look on there, and what they did is they took a couple hundred people, and what they did is they figured out the standard person's absorption of nitrogen in their blood when they're diving. And the computers, you look at the computer and you go, oh, I've got 35% nitrogen in my blood right now. I better not stay down very long. So here's the deal. Let's see if you can figure this out. At 100 feet, if you take a hit of air at 100 feet, and let's say you breathe in a liter of air, but when you exhale, less than a liter comes out. Where did the other part of the air go? And think about that. Where did the other part of the air go? Well, you have to remember, at depth, high pressure, low temperature, the other part of the air was very soluble and it got dissolved in your blood. So the longer you stay down, the more dissolved nitrogen goes in your blood. And that's a problem. You can't stay down until it hits 100% or you're in big trouble. So here's the deal. How come so much dissolved gas is in your blood? Because of high pressure, low temperature. You have to come up, breathing regular, like Boyles Law said, but then you have to stop about 15 feet before you get to the surface and just breathe in and out. It's called a safety stop. And some of that gas, some of that nitrogen gas that's dissolved in your blood will simply come out very slowly. Okay? Now, I'm going to tell you a story. This story happened in the Cayman Islands. Little Cayman, to be exact. Little Cayman Island has one of the greatest walls in the world, from about 40 feet down to hundreds and hundreds of feet. So my friend and I were diving, and a doctor and his wife were on board. And Chris, our dive master, said, this dive, we're going to go 80 feet for 20 minutes. Okay, no big deal. So my friend and I, 80 feet, around 20 minutes. But when we looked down, the doctor was down about 100 feet. And so we slowly came up, did our safety stop, came to the boat, because we're going to do a second dive. But you have to wait to try to get the gases out of your blood first. So Chris, our dive master, said, hey, listen, I said 80 feet. And he goes, no big deal, I know what I'm doing. Okay. So our second dive, about 45 minutes later, we tried to get most of the nitrogen gas out of our blood, but we still have some in there. So that's why your second dive has to be a little bit shallower and a little bit shorter. So we go in, this dive was 60 feet for 20 minutes. So we go in, we look down again, there's the doctor about 80 to 90 feet down. And finally, we come up to a safety stop, try to get some of the gas out, go to the ship, and Chris said, you will not dive with me again, you broke the rules again. He goes, I'm healthy, and look, my dive computer says I'm okay with nitrogen gas. I don't have a super lot of nitrogen gas in my blood. I said, okay. So we go back to our cottages on Little Cayman Island, and my friend and I are staying in one, and we get a knock on the door, and it's this doctor's wife, and she's crying. She goes, something's wrong with my husband. So we run over there, and we look, and he's laying in bed, and he's throwing up. And we're going, what's wrong? And he goes, my fingers and toes are numb, and I feel tingles going up my arms and legs. Well, what happened was his dive computer said he was okay with the dissolved nitrogen gas in his blood, but he didn't tell anybody that he had the flu for 2 weeks and he was super dehydrated. The less fluid you have in your blood, the quicker your blood gets full of nitrogen gas. So one of the big deal about scuba diving is you always drink tons and tons of water to get more liquid in your blood so it can handle more dissolved gas. Well, he didn't tell anybody. So what's going on is this. He is at sea level. He had too much nitrogen gas dissolved in his blood, but now the temperature is high and the pressure is low. The solubility of the nitrogen gas in his blood is very low. So bubbles of nitrogen gas start coming out of his blood. And guess where they got trapped? In his fingers and in his toes. So that's why they feel numb. And he's starting to feel numbness creeping up because there's so much dissolved nitrogen in his blood that's coming out that it's creeping up his arms and legs. And this could be a death sentence. So we said, oh my God, he's having real big problems. We got to call Grand Cayman and get a flight from Grand Cayman to Little Cayman. So we did. The plane comes over, and we had to take one of the seats out because he couldn't sit up because he was throwing up so much. So we put him sideways in the plane. Now, the plane just skimmed the waves on the way back to Grand Cayman. Why didn't it go up like normal 10,000, 15,000 feet and then down? Well, you got to remember, the higher you go in the atmosphere, the less pressure. And the less pressure, the less soluble nitrogen gas is, and it will even come out more. So this guy is hurting. He's got nitrogen bubbles all over his body. So they land in Grand Cayman, and they immediately rush him to something called a decompression chamber. Or another name is a hyperbaric chamber. This one you see here is a very large one. And think about the conditions inside the hyperbaric chamber if you want to squeeze the nitrogen bubbles back into the blood. Well, of course, it is a bit chilly in there, about 50 degrees, and they increase the atmospheric pressure to about 4 atmospheres. And this guy had to stay in there for roughly about 18 hours. Now, once the 18 hours is up and they think the nitrogen bubbles have been squeezed back into the blood, they ever so slowly raise the temperature a little bit and also decrease the pressure. But it takes about 24 hours, and usually there is some type of damage to the nerves in the fingers and the toes. So coming up, you're going to see a smaller version right here. This is only a one person. They put them in there, and you can see the controls for the pressure and the temperature. So this guy spent at least 24 hours in there. And there is a name for this disease when you get nitrogen bubbles in your blood. It's called decompression sickness, or the BENZ. And the reason it was called the BENZ is a long, long time ago, like in 1650, 1660, when they were building bridges, they would put the workers down below the water line to work on the base of the bridges, and it was pressurized air that they were breathing. And so sometimes when they came up, they had air bubbles in their blood, and it would bend them over because they'd be in the spine, hence the name the BENZ. And you aren't going to believe this one. The first scientist in like 1650, 1660 that started to work on this BENZ thing, or decompression sickness, was none other than our boy Robert Boyle of Boyles Law, way back then. Amazing. Yeah, and I guess this guy had pretty heavy duty hair, maybe 1.5 feet long. Wow. So now let's fast forward to about 1869, and what you're looking at is the making of the Brooklyn Bridge. Now, this Brooklyn Bridge, this killed quite a few workers because they got decompression sickness because the bases were way, way underground and they breathed pressurized air. And finally, after the bridge was complete, the guy that constructed it also contracted decompression sickness, but he did survive. Now, this was a crazy bridge. At the time, it was the longest suspension bridge in the world. It was about 127 feet above the river, and it was the tallest building in New York City at the time. And amazingly enough, people were afraid to walk across it because it was so long. So they had to get Barnum and Bailey elephants from the circus to walk across it first. Then once the people saw that the bridge didn't collapse under the elephant's weight, then they started going across it in carriages and horses. So now you're going to solve this next problem. Here's the problem. You're looking at some manta rays. We were diving off the big island of Hawaii. All right. And we got some great shots of the manta rays. And then what the person said, our dive master said, is no matter what you do after you've gone diving, do not go up to the top of Mauna Loa and Mauna Kea. So Mauna Loa and Mauna Kea are volcanoes, and Mauna Loa is 13,677 feet. You can't actually go up that high, but you can drive up to about 10,000 feet. So my question to you is, after scuba diving, why did they tell us not to drive up to Mauna Loa or Mauna Kea? So you are going to email me with your answer. So I hope you understand this one. Good luck. So this is a picture of our scuba diving gang. I'm lower left, of course, looking crazy. But here is the last question I'm going to ask you. Why, after you've gone diving, when you come back up, why shouldn't you take a hot shower or do a lot of physical activities, or like taking a run, push-ups, pull-ups, etc.? Why shouldn't you do that? My last question. Email me if you think you have the answer. Thanks for watching. Hopefully see you soon.